This is the beginning of Chapter 3, which is about numerically summarizing data. Section 3.1 is about measures of central tendency. If a measure of central tendency is just a value at the center or at the middle of a data set. We use measures of central tendency to help describe the characteristics of a data set. For example, the frequency distribution that we constructed back in Chapter 2 for the time between eruptions for the Old Faithful geyser in Wyoming, we can look at where is the main part of the data. In other words, where is the center of our data set? That's what we're talking about when we're talking about measures of central tendency. Where is really the middle of these data values? And if we look at this frequency distribution, we can see that the data is grouped more in this range, say between 700 and 729, than it is on this end over here. There are many more data values over here. So we could make a guess that the center of this data set might be somewhere in the middle of this area. So it may be somewhere between 710 and 719. Another way we can look for central tendency in a data set is to look at a histogram. This histogram shows that the class with the highest frequency is this one. And since our distribution decreases on either side of this, we would say that the center of our data set is going to be pretty close to 3. Here's another example. If we're looking at a stem and leaf plot, again, a stem and leaf plot gives us the same picture as a histogram, it's just turned on its side. So looking at this one, again, we can see that the class here with the highest frequency goes from 30 up to 39. So we've got a lot of the data here between 20 and 39. After that, it starts to decrease pretty sharply. So again, we could make a guess that the center of this data set is somewhere in this area, say approximately 30. So the arithmetic mean is a measure of central tendency. It's obtained by adding the values and dividing the total by the number of values. So it's what most people would call an average. And from this point on, we will refer to this value simply as the mean instead of saying the arithmetic mean. We have two different kinds of means depending on what type of data we're looking at. The population mean, which is a parameter, is represented by the symbol mu, that's a Greek letter, and the sample mean, which is a statistic, is represented by the symbol x bar. One advantage of the mean as a measure of central tendency is that it takes every data value into account. A disadvantage of the mean as a measure of central tendency is that extreme data values can affect it dramatically. Here's some of the notation that we'll be using. So the symbols below here are used frequently in statistics formulas. This is actually a Greek capital letter S, or sigma. This denotes the sum of a set of values. So this tells you add up all of the values. X is what we usually use for the variable that's representing our individual data values. N represents the number of data values in a sample, and an uppercase N represents the number of data values in a population. So here are the two formulas for the mean. This depends on whether we're finding the mean for a set of sample data or for a population. So if it's for a sample, then we use the notation for the sample mean, which is x bar, and this just tells us add up all the x's, which are the data values, and then divide by the number of values in the data set. So again, this just says add up all the values and divide by how many values there are. Same thing for a population mean. We use a different symbol. Normally for populations we're going to use Greek letters, and for samples we'll use English letters. So this is the letter mu, and again this is telling us to add up all the data values and then divide by, in this case, the size of the population. Here's some examples of calculating the mean. If we want to calculate the mean for this set of sample data, we're just going to add up all the values. So we're adding all these up, and the total is 9.89. And then there were 7 values, so we're dividing that by 7. And here are most of the digits that you would get doing this on your calculator. The rule of thumb for calculating statistics like this is to round to one more decimal place than what you have in the data. In this case, that would mean to round to 3 decimal places. So we would round this to 1.413. So there's our sample mean. Now let's calculate the mean for the same sample data, only with the extreme value of 5.40 removed. Notice that in this setup here, 5.40 is very far away from the rest of the data, so we would consider it an extreme value. If we just remove that value and then calculate the mean, our total of the values is 4.49. This time we're only dividing by 6 because we took a value out, and if we round this to 3 decimal places we get 0.748. So it did make quite a difference in the sample mean whether we had that extreme value or whether we didn't. When we had the extreme value included in the data set, that made our sample mean a lot higher than it is when we don't have that extreme value. And the median is the middle value when the original data values are arranged in order of increasing magnitude. In other words, if they're arranged in order from smallest to greatest. In your textbook, the median is represented by a capital M. An advantage of using the median as a measure of central tendency is that it is not affected by extreme values. So to find the median for a set of data, first we have to sort the values, arrange them in order from smallest to greatest, and then how many values we have determines what we do with them. If we have an odd number of data values, then the median is the number located exactly in the middle of the list. The position that it will be in the list we can find by taking n plus 1 and dividing that by 2. If we have an even number of data values, then there are actually 2 numbers that are in the middle of the list. So we find these 2 middle numbers and compute the mean of those 2 middle numbers, or in other words, the average. We go halfway between those 2 numbers that are in the middle of the list. And the positions for these 2 numbers we can find by taking n and dividing by 2. That will be the first one. And then we also take the next one. So the position for the next one would be n over 2 plus 1. Let's look at some examples. If we're going to calculate the median for this sample data, first we have to sort it. So we're going from least to greatest here. And then we have to look at how many values we have. Since we have 7 values, that's an odd number, and that means we can just pick out the number that's in exactly the middle of the list, and that will be our median. When we have a small list like this, it's pretty easy to tell which one's in the middle. It would be this one. But if we have a larger data set, it's not so easy to pick out. So if we want to calculate the position for the middle of the list, we'd take n plus 1 and divide by 2. N plus 1 would be 8. If we divide that by 2, we get 4. So that means our median would be in the 4th position. 1, 2, 3, 4. So our median would be 0.73. Now again, we're going to remove our extreme value of 5.4 and calculate the median with the remaining data. Now, if we sort it again, first, we only have 6 values, so we have an even number, and that means the median is the average of the 2 middle values. The 2 values in the middle of the list would be the 0.66 and the 0.73, so we're going to average those two. And again, the positions of these two we get by taking n over 2, which would give us 3, and then adding 1 to that, which would give us 4. So the 0.66 is in the 3rd position, the 0.73 is in the 4th position. If we average our 0.66 and 0.73, we get 0.695. And again, for the median, just like we did for the mean, if we need to round values, we round them to 1 decimal place further than what we had in the data. In this data, the most decimal places we had was 2, so we're going to round this to 3 decimal places. As I said before, if we have a large list of data values, it's not always easy to just look at the list and pick out the middle. So let's just look at how we would find the median for a list of 226 data values. Of course, first we would have to sort the list. Now, since there are an even number of data values, we need to find the positions for the values that we're going to average. So we're going to take the 2 numbers in the middle. The first one would be at the n over 2 position, which would be 226 divided by 2, which is 113. So we take the one in the 113th position, and then the next one, which would be the one in the 114th position. So we would find the values in those 2 positions and average them, and that would be our median. Now, what if we had a list of 301 data values? Since now we have an odd number of data values, we just need to find where the exact middle of the list is. So again, we sort the list first, and then since we have an odd number of data values, the median is the value in the position n plus 1 over 2. So if we take 301 plus 1 and divide that by 2, we get 151. So our median would be the number in the 151st position in our sorted list. When we talk about resistance, if we're looking at a numerical summary of data, it's said to be resistance if extreme values, so very large or very small values relative to the data, do not affect its value substantially. In other words, it's resistant to being affected by extreme values. Now, as we talked about before, the mean is not resistant because extreme values do have a significant effect on its value. The median is considered resistant because extreme values do not have a significant effect on its value. So looking at the calculations that we did in the previous examples, we calculated the mean and the median for 2 different sets of data. This was the first one where we had an extreme value of 5.40, and we calculated our mean as being 1.413 and the median was 0.73. When we took out the extreme value of 5.40, the mean became 0.748 and the median became 0.695. So the presence of the extreme value in this set of data increased the mean by 0.665, which is very significant considering the values for these sets of data. So in this case, by putting the 5.40 back in, the mean went from 0.748 all the way up to 1.413. It almost doubled. But the median only increases by 0.035. It goes from 0.695 up to 0.73. So there's not a significant effect on the value of the median. Actually, the only reason that the median is affected is because we're adding another value, and that actually changes the position of the median in the list. So it changes where it is. Now, what do measures of center have to do with the shape of our distribution? If we have a bell-shaped symmetric distribution, then the mean and the median are going to be approximately equal. So here's what we mean by a bell-shaped distribution again. We have a high point in the middle, and the distribution decreases on either side. And in this case, the distribution is approximately symmetric on either side of the highest point in the middle. So here, the mean is usually approximately equal to the median. Here's another distribution that's approximately bell-shaped. So again, our mean and our median would probably both be approximately in the middle of this and approximately equal. And actually in this case, the mean and the median turn out to be exactly the same number, which is 3.0. Here's another distribution that's approximately bell-shaped, so the mean and the median should be approximately equal. In this case, it turns out the mean is 5.52 and the median is 5.54, so they are very close together. Now, if you read the textbook about distribution shape, it will tell you that the relative positions of the mean and the median are good clues to the skewness of the distribution. Now, this is only a rule of thumb, and by itself it is not at all a reliable way to determine distribution shape. You can find all kinds of examples where this doesn't work. So we are not going to use this as a way to determine the shape of a distribution or the skewness. Here are a couple of examples. Looking at this histogram, here we would have a distribution that is skewed to the right. Remember that being skewed to the right means that there's a longer tail on the right and that the majority of the data is on the left. So this one is skewed right, and actually in this case the mean is smaller than the median, so the mean is to the left of the median. Here's another distribution. This one would actually be skewed left because again there's a longer tail on the left end and the bulk of the data is more to the right side. If we calculate the mean and the median for this data, again here the mean is actually smaller than the median, so the mean is to the left of the median. So really, as I said, the information in the textbook about where the mean and the median are in relationship to each other, you really cannot depend for determining whether a distribution is skewed to the left or skewed to the right. And the mode is the most frequent observation of the variable that occurs in the data set. So it's the value that occurs the most. If we look at a set of data, it can have no mode, it can have one mode, or it can actually have more than one mode. If no observation occurs more than once, we would say the data have no mode. And one thing about the mode is it's the only measure of central tendency that we can use with nominal data. So if we have qualitative data that can't be arranged in order, the only measure of the center of that data is the mode. That's the only one that makes any sense. Here's an example of finding the mode. This is our frequency distribution for the colors of plain M&Ms that we had in Chapter 2. And looking at this frequency distribution, it's pretty easy to find the mode of the color, because the mode is just going to be the color that occurred the most number of times, which was brown. Here are some more examples of finding the mode. If we look at this data set, again we're just looking for which value occurs the most number of times. And in this set, the value 1.10 occurs twice. No other value occurs more than once, so that makes 1.10 our mode. In this set of data, we have 27 that occurs 3 times. 55 also occurs 3 times. The other values don't occur that many times. So here we have 2 modes, 27 and 55, because they both occur 3 times. And finally, in this set of data, there is no value that occurs more than once, so here there is no mode.